Topic 5.2 is called Hess's Law. It's also known as the enthalpy and or energy cycles. This concept we've actually already touched on briefly in 5.1, and we're actually going to keep coming back to it because of the law of thermodynamics. So enthalpy cycles, also known as Hess's Law. This is the enthalpy change. So your delta H for any chemical reaction is independent of the route you take, provided that the starting conditions and final reactants and products are all the same. This allows for indirect measurements for all reactions that we are unable to do, and we can always find a workaround. And because of the law of thermodynamics, we can find that workaround, and because of that route, we can still figure out what the delta H is. And this is going to use the law of conservation of energy, where the enthalpy cycles and the total cycle will always equal 0. Remember, the law of conservation of energy is energy can neither be created nor destroyed, but only transferred. And it's going to go somewhere. And so if you do the cycle, well, because it's a circle's a 0, same shape, therefore you should have no net loss or gain. Okay, so first we have looking at our separate elements. So we have carbon graphite, which is in its standard state. We have H2, hydrogen gas, in its standard state. We have oxygen gas in its standard state. Those could react to make ethanol liquid and oxygen gas. So when these elements combine to make ethanol, you get a delta H. So we're going to say this is delta H1. And it is going to have negative 277 kilojoules in its delta H transfer. Then, when you react the ethanol with the oxygen, you make carbon dioxide and water. It's a combustion reaction. So we're going to burn that ethanol. Well, that will also have a delta H. And we're going to say this is delta H2. And when we burn that ethanol, it is going to release 1,367 kilojoules per mole. Now, we could take those separate elements and we could directly put them and burn them separately and make CO2 and H2O really hard, and we really actually can't do it, hence the other route. And that we're going to say is delta H3. And that is going to be negative 1,644 kilojoules. Now, follow the arrows when you're going through and doing this. When you're following the arrows, you know that the enthalpy cycle has to be 0 because it's a circle, right? So your change in delta H1 is going in one direction. Follow the arrows, you're going to add delta H2 because they're going in the same direction. Because delta H3 is going in a different direction, we actually are going to go through and we're going to subtract it. Therefore, we can manipulate this to solve for an unknown, right? So we could actually say that delta H1 plus delta H2 equals delta H3, which makes sense if you look at the arrows in the ladder, right? And so plug in the numbers. Negative 277 plus a negative 1367, guess what? Equals negative 1644. Hence, it's a cycle. No energy is lost. And this is going to help us to determine the stability, so on and so forth. This is a different setup than the stability diagram we had before, if you guys remember. So in the stability diagram, we had that delta H, right, the change in delta H. We put our elements up here. We put our reactants here. And then we put the products down here. This energy cycle that we have above is the exact same thing. We just draw it as a cycle to show that everything needs to relate. It actually does not matter which one you use as long as you use one of them to help direct your thinking. If you prefer the cycle, then use the cycle. If you prefer the stability diagram, use the stability diagram. What's nice about the stability diagram is because you could actually have numerical values on your delta H y-axis, it can actually give you an easily read numerical value of stability of your elements, reactants, or products, whereas the cycle just shows you that it's cyclic in nature. Okay, so how does this actually work? And this has a lot of writing, so I apologize. We have a reaction, and the ultimate reaction we are looking for is sulfur reacts with oxygen to make sulfur dioxide. But again, we can't really do this in lab, so we have to find an alternate route, right? So what we do in lab is we say sulfur reacts with 3/2 of oxygen, and that is actually going to make SO3. This has a delta H of negative 395 kilojoules per mole. All right, then we're going to run another reaction. Sulfur dioxide reacts with 1/2 oxygen to make sulfur trioxide. This is going to have a delta H of negative 98 kilojoules per mole. All right, so we need to make the correct Hess's law, the correct energy cycle. So we are going to say this first reaction is delta H1. The second reaction is delta H2. The third reaction is delta H3, and that is the reaction we are looking for. So we need to do some manipulation. We need to identify what is where. Okay, so is everything on the product side correct or incorrect, so on and so forth? So looking at the first reaction, S is on the product or on the reactant side. S is on the reactant side for a delta H3. Those are good. O2 is on the reactant side. O2 is on the reactant side. So delta H1 is in the correct order. We're good there. So the problem is delta H2. Here we have SO2. SO2 is on the product side of the reaction we want. It's on the reactant side of the reaction given to us. So we actually need to reverse this reaction. So we're going to say SO3 is going to decompose into SO2 and 1/2 O2. Okay? When that happens, because we're changing the reaction, we now need to change this delta H into a positive 98 kilojoules per mole. All right, so we have now changed that. And so that SO2 is now on the correct side. So now we have SO2 on our product side for both reactions. Now you need to cancel out any commonalities. All right, so we go through and look at our delta H1 and our delta H2. I'm going to scribble out the one we rewrote so we don't get lost. Alrighty, so we only have one S on the delta H side, none on the delta H2, so that one stays. We have 3.5 oxygens on the reactant side of delta H1. We have 1.5 on delta H2. So that means that this one on the delta H2 cancels out completely. We get rid of it. And because it's half of it, we now go 2/2, in which case that just becomes 1O2 on the reactant side of delta H1. We have SO3 as a product for a delta H1. It is a reactant for delta H2. So they cancel out. Our goal is anything we have boxed is still remaining. And it is. So now that we have written the correct reaction and everything matches, we can go over and figure out how much energy was changed here. So again, we changed that delta H. So now we're going to take delta H1 plus delta H2 equals delta H3, right? So we're going to take negative 395 plus a positive 98 because we had to change the reaction, therefore we changed the sign. Add those together and we're going to get negative 297 kilojoules per mole. Okay. So standard enthalpy changes of a reaction. All right. So this again is looking at delta H theta. We looked at combustion earlier. This is just standard enthalpy changes of what we're going to be looking at formation. Because it's standard, it has to be measured under standard conditions. So again, 298 Kelvin or 25 degrees Celsius and 100 kPa or 1.00 times 10 to the 5th PA. Please, please, please know that these are the same number. If you do not know how those are the same number and you can't follow that conversion of kilopascals to pascals of this exponent, sorry, this is 10 to the 5th, did not go in right. If you can't understand scientific notation and the transfer of the kilos, please come see me so that we can work that out. So delta H theta of formation. So now we're looking at the standard enthalpy change of formation. This occurs when, again, 1 mole of the substance is formed from its elements in their standard states. The standard states is the pure form of a substance under the standard conditions. Again, you can find that in your data booklet, depending on the table in which you are using. And I believe it is table 12. Look and make sure you're using the correct ones. The measurements for these have to be taken under standard conditions. So we would not be doing a lab on this, or we're going to have a lot of error for you to talk about for a lab. But because we can do it under standard conditions, we can therefore give a measure of stability to elements, to reactants, to products, whatever it is we are looking at. And we can be using it to calculate changes for all reactions. So once we understand what the delta H of formation is from elements to their full-on compounds, we can then predict any kind of enthalpy change for any reaction. Whether or not we can run it, we can still take that measurement. Before you actually go through and calculate delta H of formation, so on and so forth, you need to know what a thermochemical equation is. So the thermochemical equation is when you have your elements going to your compounds. And then you're going to get your delta H of formation, which is in section 12 of your data booklet. Here is an example for ethanol. So ethanol is made from graphite, which is carbon, hydrogen, and oxygen. And this goes through and makes ethanol. All right? Again, based on the definition of delta H of formation, it occurs when there's 1 mole of a substance in their standard state. That means we can only have 1 mole of the product we're looking for. So we need to make sure when we go through and balance it, we only have 1 mole remaining. So we have 2 carbon, which means we need to put 2 carbon here. We have 6 hydrogen. So we're going to put a 3 here, 3 times H2. And then we have 1 oxygen, but we have O2. Well, because it's a Brinkelhoff, we can use half of an O2. And again, that is where that balancing comes in. And when you look at the delta H of formation for ethanol, you can see that it's negative 278 kilojoules per mole. You will be asked to write thermochemical equations. Okay? And so you need to know that you look at the elements that make up the compound they're asking you to write it for, find their standard states in section 12 of your data booklet, and balance for 1 mole appropriately. All right, so we're still in energy cycles. Therefore, when we're using delta HF in the standard states. We have the reaction we can actually run in the lab. So we have our reactants. We react our reactants to make products. All right? Remember, the elements that make the reactants are also the same elements that can make the products. We are looking for this, the delta H of formation for the reaction. What we need to figure out is the summation for the delta H of formation for your products and the summation for the delta H of formation of your reactants. So when we put these together, if you remember to follow the arrows, to essentially follow the arrows, you can put it together. The calculation we're going to be using is our delta H of the reaction equals the summation of the delta H of formation of your products minus the delta H of formation of your reactants. Again, you can figure this out by following the arrows and manipulating the equation. The reason we use the summation sign is we could have multiple reactants and multiple products, and it's all of them are made of the same elements, so we want to have the summation of all the energy of those elements, so on and so forth. So if you remember, delta H equals the summation of products minus the summation of reactants. That is a standard across all of this topic, no matter what we're working with. Products minus reactants. So we are going to do an example here. So we're going to calculate the delta H of reaction for C3H8 plus 5O2 makes 3CO2 plus 4H2O. What is the delta H of this reaction? You could find the delta H of formations in section 12, or you may be given it. Here, I'm going to give it to you. So, the delta H of formation for C3H8 is negative 105 kilojoules per mole. CO2 is negative 394 kilojoules per mole. H2O is negative 286 kilojoules per mole. Notice, did I give you a value for O2? Well, the delta H of formation of an element in its most stable and standard form, hence O2 gas, equals 0. So whenever you have that pure element, it equals 0. All right, so my suggestion in how to solve this is what I do and how I think about it. We are going to have our reaction, and ideally you would not have to rewrite it, but I did not think ahead. And an FYI, sometimes IB doesn't balance the reaction for you, or they don't finish balancing it for you. So always check the balancing first. Gotta love IB. Okay, I'm going to go through and I'm going to plug in the numbers that were provided to me from either section 12 of my data booklet or in the problem itself underneath the compounds they belong with. So here we have a negative 105. And this does not have, it's multiplied by 1 because we only have 1 mole of it. We have 5 oxygens and they have a value of 0. So it really doesn't mean anything. We have 3 carbon dioxides, and each of those carbon dioxides have negative 394 kilojoules per mole. We have 4 waters, and each of the 4 waters have negative 286 kilojoules per mole of energy. So now, let's calculate the delta H. Remember, the delta H of reaction equals the summation of your delta H of your formation of your products minus the delta H of formation of your reactants. What does this look like? So my products, I have 3 times negative 394 plus, because it's summation, 4 times negative 286. And then I subtract that from my 1, negative 105, because oxygen is 0. Do the math, and you get negative 2,221 kilojoules per mole. Look at your sig figs, ladies and gentlemen. Okay? In all your numbers, you only have 3 sig figs. So really, it's negative 2,220 kilojoules per mole as your correct answer of energy.